Today we're extremely happy to have Rene and Poncelet visiting us. So Rene is one of the leaders in precision calculations at the LHC, and with his collaborators has really been one of the people kind of driving this to its utmost extremes. And so for this work, he's received a bunch of awards, including the Guido Altarelli Prize and recently a ERC grant from the European Union. And so today he will tell us about some of the theory behind these calculations. So thank you.
All right, thank you very much. Also, first of all, of course, for the invitation, but also for the opportunity to speak here and present a bit of my work. So what I want to talk about is precisely that, precision phenomenology at the Large Hadron Collider. And I did something very, very scary. I start my talk with the standard model, which is kind of the standard. So yeah, the idea is that we developed over many, many, many years our fundamental understanding of the structure of our universe at the microscopic scale, which is consisting essentially out of two sets of particles. One set is the matter particles; these are divided in quarks and leptons, and a set of interaction particles, which are the gauge bosons as well as the Higgs boson. This model is, of course, your phones, or now probably well, essentially has been surviving any tests we have put it to. So what in collider experiment. So the idea is here that we are measuring high energetic scattering of particles and measuring the outcomes of these collisions in terms of cross sections. On the right hand side, I show you a summary plot from the Atlas collaboration here, you know as well. Which shows all these measurements for various standard model processes happening at high energies. And it shows on one hand the cross-section measured at various set of mass energies and compares them to the theory prediction from the standard model. Theory predictions are those behind. This comparison in this plot looks very, very much consistent with the standard model. And when we're talking about consistency, we typically have two things in mind. One thing is that it reproduces the central value in these measurements, right? So we're predicting the central value, and the agreement is within the uncertainties. One set of uncertainties are, of course, experimental uncertainties. Another set, theoretical uncertainties. And in this talk, I want to precisely discuss, first of all, how we achieve precise predictions for the theory. And in the second hand, I want to discuss the later part of the talk. I want to discuss how we can derive reliable uncertainties to make these comparisons feasible. Okay, so eventually, if you want to make theory predictions, what we want to do is we want to kind of model somehow these very, very complicated collisions. So it's like a picture of a Higgs plus W event, including all the radiation which goes around it, and these are very complicated signatures. We kind of want to get them from a theoretical prediction. The way to do this in practice is we employ the principle of factorization. Okay, what we can do, because we cannot solve the underlying equations for the full generality for this kind of processes, but we have to do some certain approximations, and factorization is our guiding principle for this. And the idea is simply that what we can do in a precise manner is that we can separate different processes happening at different energy scales. We can start at the very high energy scale, for example, and taking now QCD as an example, where we can looking at fixed order perturbation theory. So we have a high transverse momentum square, and we can view these processes as a scattering of individual particles. These, of course, coming out with very high energy in these kind of small multiplicity processes, and this energy is then radiated off in a shower of particles, which eventually transforms into a set of particles which we measure in the detector. The immediate stage we typically model in terms of resummation or parton shower. So this is the idea. Be bridging the gap from this very high energetic state to a low energy state by using resummation, which allows us to resum all the large contributions that are rising. And in the end, we have some non-perturbative physics going on, which we model with phenomenological models. This is the organization phase, simplified. Okay. The first part, my talk will mainly focus on the first part, which are fixed order perturbation theory, because this is the part of the component which is really relevant, setting the precision of these calculations. There are, as I mentioned, various other components which also, of course, important to reach precision, but the fixed order perturbation theory in the end will always set the overall scale of precision we can potentially achieve, right? If we are not particularly precise here, anything else will not help us all, will not help us at all. So that's the reason why I will focus on this specifically. I will touch upon resummation also. I'll give a couple of examples. And I also will give later on, as I mentioned before, an overview of how to estimate the uncertainties from all these components. Okay, so the first question is what kind of perturbative calculations we actually need, how far you have to go in perturbation theory. And as an example, I wanted to show you here a measurement by Atlas. This is a measurement of an angular correlation observable. So this is like called the energy-energy correlator. This is essentially measuring multi-jet events. So you have this event where you have several jets in it, and you're measuring the azimuthal opening angle between these jets, and then you pin it in the histogram. The data is here shown in black. This is black dots, and the uncertainties are with bars. And in the color, you see the perturbative calculation here. This is specific for this observable. Perturbation theory is a really dominant contribution. And that's the reason why we can just directly compare it here. The bands indicating the uncertainties. So you see a leading order, next to leading order, next to leading order. Naively, we expect about the 10% next to leading order uncertainty, which is very, very represented in this picture. That's the reason why I chose it. And we're ending up with like about percent precision for next to leading order, 2-3%. And you see here really that we have to go to next to leading order to actually be at the precision which is comparable to the experimental one. You also see that if you look at the shape of the distribution, so the central values, so this differential distribution, also next to leading order is a very important correction. Like you get all these wiggles into the prediction, right? And this is like a very nice example where perturbation theory really buys you something. So this is just my statement, essentially, effectively, what we need to achieve to make really precise measurement comparisons. We need to go to next to molecules. Okay, how we get there? So there are many contributions we have to take into account. Typically, these calculations are done in collinear factorization. Collinear factorization means we're looking at the cross section. This is the object we measure. You want to predict it. You have two incoming hadrons, and you're producing some finite state X here. And we write this as a convolution of a Platonic cross-section, which I will come to in a second, and pattern distribution functions. The pattern distribution functions describing the content, the quark gluon content of the problems. So, okay, and so these are non-perturbative, right? So these we typically extract from data, or we can try to get them from lattice QCD or something like this, but eventually these are non-perturbative objects. The perturbative part is all in this Platonic cross-section, which we can then expand, for example, into strong coupling constant, right? A leading order, next leading order, next. In these symbols hidden, right, I will not go too much into the technical details there, are all kinds of contributions, right? In leading order, we have the typical tree-level type of diagrams. Next to leading order, we get contributions from additional radiation, so we emit an additional gluon in this case, or a virtual correction where we have like a virtual exchange of combining these two is a technical challenge. It's not coming for free. So you have all kinds of tricks and shenanigans to do this. But this together gives some finite result, which ends up to the next leading order. And the next leading order, essentially you just go in one more. So we have two emissions, a virtual and single emission, and a double virtual. Okay. So the challenge really, if you want to do next to order calculations, are twofold. One is typically the next to leading order, the double virtual contribution. So these diagrams, these are very, very complicated. And typically they have a very complex rational and transcendental structure. Rational meaning is a rational in kinematic invariance that appear in these expressions. And transcendental, I mean by special functions. So in these amplitudes, new functions arise whenever we go to something more complicated, which haven't even been considered mathematically. So you really have to develop typically new expressions for these and understanding how to get them. So there has been a lot of progress on this. The current frontier, I just summarized this right corner here. Sorry for it's a bit small, but essentially we have at the high multiplicity front, we have a two-loop contribution for 5-point functions. So this is like diagram, so you have 4 extended particles. At 3-loop, we can go up to 4 points, 2-to-2 scattering. And at 4-loop, actually, we can go up to 3 points. You notice how this goes, but you add the leg, you go 1 loop, and so on. And this is exactly this rational transcendental complexity, right? Here we have a very rational complexity, and here we're getting a functional complexity. Okay. Right. So this is one component. The other component is the combining these things in an infrared finite cross section. And this is actually quite non-trivial problem. It took very, very long to solve. Okay, just on a conceptual level. And if you look at the literature, you find that there's about 20 years between the first next leading order calculation, the first general implementation of schemes that can actually allow this. And they have all kinds of funny names, as I said to them. I will mainly talking about results which we drafted our group, and this is in sector proved on residue subtraction scheme. Just to mention. So I will not continue further into technical discussion. I want to show more like phenomenology and a bit of plots. And I will do this by discussing specifically jet production colliders, because this is also a topic where we're collaborating together with Ian here. So I thought it would be a good idea to highlight where we have the connection. So multi-jet production specifically, right? These are essentially events where you have a lot of hadrons in the final state and you're producing a lot of radiation. It's actually a quite good probe to test specifically QCD, right? And also specifically perturbative QCD. This comes with two components. One of them is we want to test if QCD is actually realized, right? If the vertices and the interactions are as we're expecting. And on the other hand, you want to understand its parameters. So we want to extract essentially the strong coupling constant, which is the only free parameter in masses QCD. Potentially, we can also extract masses, of course, but this is from the perturbative QCD point, not the main point. The thing, one of the features here is, and why we need to do complicated computations is, if you do next to leading order theory, you will not be able to compare to data. If you do it, you see that the theory uncertainty is so much larger than what you can actually measure, because there's so much data of this type, right? That you do not really get a good handle on it. And therefore, there's a good ground for next to QCD. There has been theoretical progress. So in 2017, essentially, there was dijet computations for this kind of processes. And this kind of lead to many publications that have been used, for example, to constrain pattern distributions functions, has been checked for use to do all kinds of tests. But eventually this is a bit restricted because this is just a back-to-back kind of configuration. More recently, we also managed to go to 3-jet production. So this is this 5-point. You can imagine 2 incoming, 3 outgoing. This is the 5.2 loop case. This has been achieved recently, and then we can study more complicated observable. For example, we can do ratios of cross sections, like 3 jets over 2 jets, which are very sensitive in particular to the strong coupling constant, because you can imagine that a lot of stuff is canceling out. This is just one order in IFS higher, so it's directly proportional to IFS, which is a good example. And similar, you can study now event shapes. Event shapes are more like global observables, which depend on the kinematic of all the kind of particles. Okay, here on the right-hand side, I show you an example for such an R32 observable. You see it here. Blue is NLO and red is next to the. And you see what you can gain from going higher order perturbation theory. You get at NLO, you get a relatively large uncertainty, about 20%. And if you go to next to leading order, this kind of collapses to almost invisible in this plot. Right? So there is an error band around this. You see it in this weird fluctuation. So this is really something to be explored. Okay. Looking in a more detailed view on these event shapes, I will show you in a second two specific observables. One is the thrust and thrust minor observable. This is like thrust you may know from E plus E minus. This is something one typically learns in a particle physics course. So in E plus E minus, you're producing two jets, and the thrust essentially tells you how Poncelet-like the event topology is, how back-to-back it essentially is. A large value of thrust typically means you have like a spherical event, and the back-to-back configuration of the zero. For the and the thrust minor essentially measure exactly the orthogonal components of this. And then the energy correlator, I introduced you already to this. This is this angular observable. Precisely defined, it's like a weighted sum over all jets, and you bin all the jets with a respective angular opening. The measurement which I will, the calculation which I show you in a second has been done, in particular using jets. So you could technically think about this as particle on particle level, but we use jets here because these are better calibrated objects. So this is an experimental concern. It was an experimental concern. Okay. This is a plot where you can see how this can look like. We see here, for example, this is a thrust and this is a thrust minor. And you see different energy scales in each of the plots. You see a TeV to 1.5 TeV, 1.5 TeV to 2 TeV, and above 2 TeV. HT2. HT2 is essentially a measure of the hardness of the event. It's like the total PT in the Dijet system. And you see, you can nicely see how the higher order corrections actually help to describe the data. Okay. As you can see here, and you can also see that it helps to rescue part of the shape. Right, you see it. It's very nice. And yeah, okay, this plot I actually showed to you just a bit more detail now. So this observable is not only can be precisely measured, but it helps to disentangle also different kinematic regions, because in the center of this observable, you have essentially like isotropic events, so which are look like spherical. If you go to the right, you have essentially situations where you have a hard jet, and on the other side, the jet is splits in two. These events are collected on this side, and then you have like on this side really like a dijet configuration. You have two hard jets and a small lower PT jet from the center region. And yeah, so this is just to say that actually you get a description all over the phase space, not in like some corner, but it's like really. You can do the same then also even more differentially. Now this is I mean, this was just this like a lower cut on HT2, but you can do it of course in bins, and you see that you actually describe it across various scales of hardness, and you get a very nice description. This nice description then can then be turned around, for example, to extract a strong coupling constant, because this as well is defined as an R3 to ratio, and you can extract the strong coupling constant. So this is an example how this might look like. So these are all kinds of atlas measurements and CMS measurements, even the zeros there, of the strong coupling constant at various energy scales. So this is all high energy. And here are the blue points. These are the extraction from the specific set of observables I showed to you. These are the blue ones. On the left-hand side, you see what you get if you do NLO-QCD theory. And this yellow band is the uncertainty from that measurement. If you do it next order QCD, you see it, what you can gain, right? So it's much smaller. You nail it really down. Okay. Well, by now it's a bit outdated. There are even better measurements now. But this is just like where I'm coming from. Okay, good. So this was about mostly about fixed order perturbation theory. But as of course, this cannot work for all kinds of configurations. There are many kinematic regions where like just fixed order calculation will not cut it, and you will need a more complete picture. The problem is if you want to do it at high perturbative order and match it to, say, a parton shower, there are all kinds of technical challenges which are still unknown and have not been solved. So one has to play a bit and see what one can actually achieve. And there's one way one can do something more than just these simple fixed order predictions by shortcutting, say, this whole event simulation in terms of so-called fragmentation process. The idea is here that whatever that in the end, the simple picture we have in mind is, for example, you have a quark here or a gluon, and we know if it's high energy, and it will at some point form, after all the shower, will form some identifiable object, say a hadron, let's say a B hadron, a D hadron, right? And the idea is to incorporate all this evolution in terms of a D-glub, in terms of D-glub equations, and a non-perturbative function that describes this transition. This has been done a lot in E plus E minus. This was like the typical thing one did there. For example, when studied the B hadron production at E plus E minus, and you really factorize your cross-section in terms of the platonic part, which now depends on the momentum fraction and the transition of a parton to a hadron, which is a non-perturbative function. And this can be used to describe such processes even without using actual fully event simulation, but you get a handle on this kind of more exclusive things. And this is something we achieved more or less recently. Terry Generati, his collaborator, is also joined me here. He was mainly responsible for implementing all the nasty stuff. So we achieved essentially such kind of computations through next to leading order accuracy for different signatures. Just show here two examples. On the left-hand side, we show like pion production in PP. This is like pi zero production up to very low PT, and we show again leading order, next to leading order here compared to data. And here we show the impact of the non-perturbative fragmentation function on the prediction, right? This is shown here compared to data. In this specific example, for example, we could say, probably this fragmentation set doesn't work very well. Good. What's the final outcome of that? This was another on the right hand side. We have a different process like this, just open bottom production. Right, this is something like reducing a pair of heavy flavor quarks or hadrons in this case, and then you're looking at this PT spectrum. For example, you again see using next to leading order. Really, gives the description. Here's the reduction uncertainty is not super great, only at high energies. They narrows a little bit. But this is kind of expected because it's a very low scale process. Okay. This brings me a bit to my connection to Ian, collaborator. So another way to use this, for example, is to use to study the production of small radius jets or jet substructure in more general. And the idea is here that we noticed a couple of years ago that if you look at these fragmentation or this factorized structure of the cross section, that this part, this we computed before, this is essentially the object which we managed to calculate in the fragmentation processes, that this can be cast in such a way that we can include the essentially what is called a semi-inclusive jet function, which is a function which describes the transition of a parton into a jet of a certain radius. And this is quite nice because essentially what we can do, we can resum, in this case, specifically logarithms that arise from the radius. There's some technical details, there's a modified RGE here involved. So this is not D-glub actually, so we have to do more work. But I mean, this is like it's a technical detail, which comes again, theory-wise, very interesting, but okay. For the pheno, not so super relevant. And the interesting thing is, this is not only for this semi-inclusive jet function, there are all kinds of objects one can think about how a parton transitions into some object which we then identify, or some observable which we want to measure. So for example, energy correlator specifically, or by a similar factorization, which might be interesting for the future. But back to the small R jets. So this is shown here. This is shown here. So we have a comparison here against Atlas data, CMS data, sorry, in this case. And this is for different jet radii. So this is a very small radius, 0.1. On the right hand side is a slightly larger one. And I just wanted to quickly focus. I come back to this anyway in more detail later. Focus here on this this example here, where you really can see that the next to leading order, this is the red one, it describes the data within its uncertainties. That's okay. But using also this resumming of the small r logarithms, you really see that you can describe the shape even better. That you can have a small uncertainty and you get the shape even better. So this is something quite remarkable. And actually a quite differential measure. Okay, so this brings me to the second part of the talk. I want to discuss a bit further, or a bit more detail, how these uncertainty bands, which we put on these plots, coming into being. Okay, because actually this is a topic which was hovering around as a background since ever we started this kind of computations, but most importantly, it was always like a bit, yeah, you do something and getting a band, and more recently, it come more and more to focus, to think about more clearly or more carefully about how we do this theory and so. And there are all kinds of developments which I want to detail. So when I'm talking about theory uncertainties, there are different sources of them. One, of course, a couple of them are quite easy to understand. One is, of course, parametric uncertainties. What's the value of the strong coupling constant? There's an uncertainty to it, so you can be easily propagated to the result. Similar pattern distribution functions. So their uncertainties, they're well understood prescriptions on how to propagate these uncertainties to the final result. Another source is, of course, non-perturbative parameters in Monte Carlo simulations. I don't talk about them. If they are in dominant effect, that's not good for you. Then you typically cannot do very much precision physics. Let's put it like this. Or you can use whatever you're looking at precisely to constrain those parameters in these models or distinguish different. The thing I want to most importantly talk about is these the effect of missing higher orders. So as we go to next living order, but of course we are missing the QPO, what's the bottom 4 effect, and so on and so forth. So how we can use this to, how we can predict the impact of that. And the problem here is really that if you want to estimate something which we don't know, right? Because if you can go to a higher order to estimate the impact of that, well, then you can just right away use that, right? So it's kind of fun. Try to estimate something you don't know. Just to write a bit in formal terms, it's as an example. So let's imagine we have a generic perturbative expansion of some coupling parameter, and f are our coefficients. So alpha here could be the strong coupling constant, for example, but I just write it here as a generic coupling. If you talk about leading order, we take the first term. Okay, that's trivial. I introduce a small notation here. These f hats here mean that there's an that we actually have computed this. That we actually know this. That if I drop the f, if I remove the f, the hat from the f, that means I don't know the actual value of it. It's just like a parameter, a placeholder for this value. And this is essentially what we want to do. So we want to compute, say, leading order +1, so +1 term which we don't know, and the assumption that the next term is the most dominant one. Otherwise, we have to take. And yeah, next leading order, next. So how do we get these coefficients with our computing? Previously, so this was typically done in all these plots, is you're using scale variations. So this you probably have heard. So the idea is, okay, you have the expansion in the strong coupling constant. So for example, we know how this cross-section behaves as a function of the renormalization scale. So this is a scale which appears in the calculation. We know it's going of higher order in alpha s than what you had before. So that's amazing. That means if we study the dependence on the scale choices in our calculations, we learn something about this missing higher order terms. Okay. The problem is here that we still need to invent some prescription because it's not clear how to do it in practice. Typically, what one does is one chooses some central scale choice due to some reason, and then do some variation. It takes the envelope uncertainty. This is shown here. So this is the actual function form. You do some computations, and you take the error band to uncertainty. This is what we in all the plots I showed you before how serial uncertainty came to be. Okay, precisely by this prescription. The problem is it's not always reliable. There are many examples where we know it doesn't work and the uncertainties are underestimated or overestimated. And also, yeah, some of them can be explained, some of these cases, so one can design workarounds, but not everything. There's some fundamental issues in terms of the philosophy, because the scale is not a physical observable. It's just an unphysical parameter, which just appears in the calculation during the renormalization process. So you cannot extract a true value to this. This is a problem. And also it's very difficult to assign any statistical interpretation to the result, because it's just a systematic variation as a function for. That's probably something experimentalists are very angry about when they get scared. So they cannot really use it. And then the last thing is a bit more subtle is what about correlation? So if you have several bins, do you treat them correlated, uncorrelated? How does it behave? And does actually scale variation correctly reproduce the uncertainty? Anyway, there's a correlation of the uncertainties into bins. The different approaches under investigation to overcome some of these issues. And I will specifically talk about this serial nuisance parameter approach, which become more say, what do you say, fashionable recently. So that's it. So the idea is here that, okay, kind of dumb. So you say, okay, the thing I don't know, I parameterize by a function of parameters, serial nuisance parameters. Okay, it's also far so trivial. It's probably complicated to do so. In particular, you don't really, I mean, the assumption is here, I can find such a parameterization, right? Such that there is actually a true value of my parameter theta. Okay, so I represent my object I don't know. It's a function of some parameters, random parameters. And it's done such that there's a true value. So if I do the actual calculation of the next order, I actually find my true values of thetas. This might be in practice infeasibly complicated, or even more complicated than doing the actual calculation. But we will see there are some ways around this. And then a second aspect is that we want that these are kind of random parameters, they have some distribution, some prior distribution. And in the best case, we want to know it. Right? In the end, we want to map it to some Gaussian, 1 sigma Gaussian. Exactly. And, so this is the basic idea. How to achieve this might be very complicated. I will come up with a couple of examples where we can actually work it out. The first example is also, I guess, the original one, is the idea to apply to a resum cross-section. This is, for example, for the transverse momentum resummation. The cross-section at leading power can be written as some convolution of different terms. Okay, that's not so important. Crucial is that the actual ingredients in this calculation, so H, this gammas, and the also the Cosmos that these are actually scalar series. So here, if you go through it, you will in the end we see a series in alpha S, and all the terms here are just numbers in this case. Okay, just like 5, 7, pi. Yeah, so something simple. So the only thing really what you have to do in this case is you have to find a proper normalization and then to get the proper distribution. And this has been worked out for this case by Packman. He figured out the normalization. We exactly achieved this. So he did a survey over many computations, right? Using his way of normalizing things. He figured actually out, oh, okay, I get kind of a Gaussian distribution of the actual calculations. Sounds a bit weird, but this is what came out. He turned it then around, saying, okay, I assuming now that this distribution holds also for terms I haven't yet computed. And then he was able to assign uncertainty by using this distribution for the next order he didn't know. But by this, propagating a theory uncertainty. I will jump over this. Say there's just to say there are some subtleties where this is not always so easy. And coming to something I've been working on. So this is this approach worked in that case very well because it's relatively simple. The objects are very simple. And our fixed order case, which are very dear to my heart, the problem there is you don't know. You don't even know what is the functional space of functions that appear in next order necessarily. It can be very complicated. So we cannot really do it. And here the idea was like to do some effective way by identifying objects which are of order 1 in the sense to get something like a Gaussian distribution. And what we figured is if you do a very naive normalization, this is essentially pulling out the Toft coupling out of the perturbative expansion, then we're getting these ratios, and these ratios actually behave like order 1 quantities. We did this by testing many of our calculations to see that this is actually the case. And then the idea arises that, okay, our estimate for the next order is by using some random function, this one, and these lower order coefficients as input to derive an estimate for the next order. This is of course not quite the original idea because of course we don't have an actually true parameter theta hat here. Right? This is because in an approximate effective way, we don't really have this. Still, I want to convince you with a couple of plots that actually this works actually quite well. First of all, this is just a set of processes where we tested this. Details do not matter, but it's different signatures. So from Higgs production, über boson pair production, TT bar, multi-jet production, photon plus jet, and so on. And what we did is doing the same thing. So we extracted these parameters, which the random parameters, and we get again a Gaussian distribution in this case. And this we turned around to do then our uncertainty estimate. An example is now this TEC, which we saw now a couple of times. This is for this as well. Here again, I have scale variations. These are different HT2 bins. Sorry, they're cut off. And you see here the uncertainty from TP. There's different ways to propagate the uncertainty. One is like adding variations in quadrature, and this is like a replica approach where you do like propagating all kinds of functions. Just to visualize, this is a bit more conservative. This is more realistic. And yeah, what you see in this case actually, with what we expected, we get a consistent picture with scale variation, because in this case, actually scale variation worked. Another example is jet production. So we had this inclusive jet production. We had this already. The reason why I picked this is there's very peculiar behavior in terms of theory uncertainties in this case. And the reason here is, the point here is that if you look at jet production as a function of the opening angle R, you see that there's a funny behavior of uncertainty. Here on the right-hand side, this is next to leading order. Sorry for the color flipping. And you see that the band here gives you uncertainty. You see that suddenly there's some kind of collapse of the uncertainty at some point. And this is actually around 0.4, 0.5, so which is the typical value while achieving jets use. And this is kind of probably related to accidental cancellation happening if you do scale variation. So these estimates are coming from scale variation. So this would be an example where might be a different way, a different prescription of using zero uncertainty would help. And just to highlight where the problem of scale variation comes really into being, this example, this is for R.4 and this is R.0.7. And you really see, for example, the NLO uncertainty here does not capture at all the next leading order correction, completely moving outside. So you completely underestimate it. And in this case, for example, the scale uncertainty is super tiny. It's very, very, very small. And maybe unrealistically small. You can solve a bit of the problem by going to resummation. So because this will break some of the degeneracy. So you get here, these two plots here, this using the small r resummation, which we had before. These are essentially showing that you can actually resolve some of the accidental calculation, get much more sensible theoretical uncertainty. Right? Also, you see that it works as you would expect, right? So you really see that the uncertainty band, here this is the comparison directed to next leading order and resummation, is much more consistent for different radii using the resummation. right? So there is really something going on with the serial uncertainty estimate. And if you do it with TMP, you're getting a very interesting picture. So this is the TMPs now here for the 0.4 case. You really see that you get much larger uncertainties at next to leading order and more more realistic uncertainties next to leading. And this is just for fixed order, pretty perturbative, and this is with resummation. So you're just here reproducing this plot more or less, which is nice. And if you do it for the 0.7 jets, again, you're improving, you're getting now much more sensible. So here for this one, and you get a corresponding perturbative stable prediction for the resumptions. So that's very nice. This was, of course, this was using this very approximate effective approach, which I showed before. So this is like quite ad hoc, but still does work quite well. Terry sat down and he was like, I'm not happy with this. I calculated in a more complicated way. So he really sat down and figured out a way to actually incorporate the original idea, to really break it down to individual components and vary them in a very neat way. So key observation is that you can break it down into different prediction, different Mellon moments. This is not so important. Crucially is here that you can write essentially the cross-section as objects, which again represent, similar to what we have seen before, as scalar series. So this is for the beam function. There's some approximation one has to do because in the full generality it's a bit complicated, but you can get a very good approximation to the actual structure. And the crucial point is if you propagate it through as an uncertainty, you again get an improvement in terms of sensibility of the uncertainties. First of all, you see this is again for very small radius jets, so you're expecting really that fixed order fails here, right? And if you do a scale variation, things are a bit on the edge here, and you get very large corrections. With the TMPs, these TMPs uncertainties on the right, you're getting much larger uncertainty here, as you would expect. The resummation does not change much, right? The only thing which really changes is that the leading order plus AA is much larger and now giving a consistent result. But still nice. And you can really see now the massive impact at small r of the resummation, where you would really expect that it brings you something. So this is the comparison directly of fixed order versus the result gate. It's a bit here, so it looks extremely dramatic. If you go a bit to larger r, where we saw this problems of very small uncertainties, you really see now that you also improve on this. So this is a fixed order case now. This looks good. And also you see that you get like a very nice consistent picture. Okay. Yeah, so with this, I will come to the close. I hope I could convince you that you have to go to very high perturbative order to get accurate and precise predictions, which can take really advantage of the amount of data we have. And you can apply these kind of things are not only true for the jet production for many processes, and this can then turn around to do all kinds of precision measurements, not only like doing the test, but also to extract these parameters in a precise manner. I also discussed that you can look at even exclusive observables using this fragmentation approach, right, and resumming certain components and getting also precise predictions for these kind of things, which are typically out of the realm of fixed order QCD. It would normally require a much more general picture. I also moved into the theory uncertainties. So the point is here that this topic of how to estimate uncertainty becomes more and more important. It was a bit neglected over the years. Now it's become a major thing again. So looking forward to more and more result there. And yeah, looking to the future, the two major things. One thing is multi-loop amplitudes are needed to compute more processes. So to extend the list of processes, I just showed here a more or less complete list of all final state which have been calculated through next to order over the years. But these are all like relatively low multiplicity. If you go to more higher multiplicity, you need more of these multi-loop amplitudes, and this is a challenge. The second thing is, matching these calculations to a parton shower properly, so that you get next to event simulations, is a major big breakthrough if you're going to manage it something. And this is thank you very much for attention.
Yeah, this is a pretty broad question. So I think, can you go back one slide?
Sure.
So this is going to be a little bit for the sake of argument, but maybe in that top left plot, there's maybe a tiny deviation at the high PT between the NNL prediction, and the data. At what point can you start to parameterize these deviations in terms of like BSM physics? So like, do we have the theory prediction in order to turn this into a BSM interpretation?
Okay, very good. So I think there are two types of interpretations typically BSM, which are done in this region. So either there's a bump hunt, looking like heavy resonances or something like this. Normally, you don't rely on theory prediction too much, right? Because if you take just the spectrum from data looking like a bump on top of it, that's much more precise than if you Monte Carlo. The hope, of course, is if you really manage to go to next event simulations, that you can use more of this Monte Carlo to avoid systematic uncertainties from the experiment, right? To what extent this for specific searches really buys you something, it's hard to tell, I thought. The second thing where like these kind of predictions really buy you something already now is EFT interpretation. Because if you do an EFT interpretation, you're looking like rising tails here, and you don't really care actually about you're just looking at the difference here, right?
Yeah.
And the thing, these new predictions, those the yellow ones, these are new. These have not been used for this kind of specific case, but of course we would be happy to provide the K factors so we can do that, and to add on top some EFT operators. This would be then separate, right? But I think the red one here, this has been used in that sense already for EFT interpretations, right? So because this is like next to leading order, next to leading order, these calculations have been around a long time, and I know from people who are doing EFT interpretations, X method and so on, that they have like digit data where the residuals are computed from next to QCD for many of them, so they use it. So that's already used in that sense. And I think you could probably gain something if you use our prediction here, because you get higher sensitivity to the small uncertainties. So this would be maybe a nice application of this.
Okay, thanks.
Hope that's not it.
Oh yeah.
Yeah, sure.
You go to maybe slide 28 is a good example.
Mm-hmm.
So a simple question is, and of course, the series at some point, it stops being convergent. And so these coefficients should start growing factorially. And so my question is that you estimate uncertainty, but when you estimate uncertainty, what does the meaning have if the underlying series itself is not truly convergent? And do you start to see that? That's something.
Yes, very good point. That's a very good point. The underlying assumption here, which is an approximation, of course, is that this is convergent. That this series is convergent. This gives this an interpretation which you can use. Of course, we know, let's say, 7-loop order or whatever, right? This is going to be. The question, though, is since it's an asymptotic series, so QCD in general is an asymptotic series, you should stop as soon as you reach the point of maximal conversion, right? And afterwards, you cannot say anything because you dominate essentially real normalons and what's not going around, right? And that's where your perturbation theory stops. And then, of course, also the uncertainty estimates from this breakdown. This is
able to see like at which point.
For QCD, there was some funny estimates using the normalons propagators that it's 7-loop order. So we're talking about next to leading order being the state of the art now. So let's talk in 500 years or something like this. I don't know. The complexity of this calculations grows also factorially. right? So it's not like that if you have one order, you can easily calculate the next order. It's just like exploding in complexity. So having many of these results in QPAO even will take many years from now. So this is like many people working on this already, but it will take. I mean, as I said, 20 years to just develop the scheme, and people just started now working in the QPAO schemes. Just starting now because NNO was essentially done. And 2-loop amplitudes, 3-loop amplitudes for mighty scale processes, not even talking about that. Safe for the moment, but yeah, that's not satisfactory, of course, for all times. But yeah, for the moment, should be a good enough assumption.
Any more questions? Now let's thank the speaker again.